Hello, everyone. I'm Lexing from the Australian National University. I'm going to talk to you about captioning with knowledge and style. First, let me start with a little bit of background. I lead a computational media lab at the ANU. On a different day, I would probably be talking to you about how we understand viral videos over the past 5 years, and how we learn to love stochastic processes and marry networks with time series. Today, we're going to talk about this red blurb about captioning images. We also work on comparative summarization of documents, visualizing graphs, and humanizing machine learning. Let me first motivate this project by examining the widely used MS Code code set by others and ourselves. Here are two example images and their associated human written captions. The annotation guidelines for MS COCO explicitly states that the caption should not contain any entities and should only contain visual information that are present in the image. Another view for these captions is that because of these guidelines, they tend to be obvious to the human viewer and are stripped of any context that might emotionally engage the viewer. So for this project, let me just claim that boredom is a good motivator to try and find new approaches for making image captions more interesting. Today, I'm going to cover a slowly unfolding trilogy that a group of us have done. The first effort done in 2015 was published in 2016 is Centicap, or capturing image with sentiments. And 2 years later, we figured out how to style image captions from a large collection of romantic novels. And then 2 years after that, we captioned news images with knowledge about entities and objects in the real world. Let's start from sentiments, which is a thought view or attitude that are based on mainly on emotions instead of reasons. So a computational, highly simplified view for sentiments can be that it can be divided into the positive or negative polarity. And when we see the same image described as a tasty burger or overcooked burger, for example, that will highly influence our decision making, such as whether or not to go to this restaurant and order food. So in the natural language processing and information retrieval literature, there has been a lot of work pioneered by Biparin and her PhD thesis in the early 2000s on sentiment analysis, basically extracting and inferring statistics of public sentiment from large text collections from all different sources. And here I would in particular mention one work that has informed ours that basically combines sentimental adjectives with nouns to make sentiments recognizable from images, done by the Columbia Digital Video Lab. So the open challenge we faced in 2015 was to synthesize appropriate sentiments in a sentence that are also grounded on an image. We meandered through many modeling choices in 2015, but in hindsight, the joint CNN-RNN architecture newly proposed at that time, called show and tell, would have been the obvious choice. So grounded on this, there are still three open challenges. The first one is representation. Basically, how do we encode sentiments in a show and tell like architecture? The second one is training. How do we appropriately learn, make the neural networks learn about sentiments if we do not have a budget or amount of data that are comparable to MS COCO. The last one is evaluation, right? So we um, cannot can no longer only rely on n-gram metrics such as blue and rouge. Then how can we tell that we're doing well? We start by solving the data collection problem by building a parallel data set on MS Coco um, on Mechanical Turk. So we asked Turkers to essentially replace or rewrite any of the MS Coco ground truth captions using one or more of the adjective noun pairs that apply to the nouns in those sentences. So we also specify the sentiment polarity. So the resulting, as you can see, the word pairs are either all positive or all negative. So this is in fact our third iteration of the data collection task. It started generating sentences or captions that are too verbose, and then two terse, and this particular task generated captions that are just right. So we collected about 3,000 image caption polarity tuples, which is about 1.5% of MS Coco, and it costed about $1,000. The talkers loved this task, though. They wrote back to us saying they enjoyed it, which we're happy to hear. So here's the overview of the Centicap model. From a few pages ago, you can see this is essentially two copies of the show and tell model, where the top half is exactly the show and tell model trained on MS Coco itself, the blue half, and the bottom green half is the same as show and tell architecture, but fine-tuned on the set of sentimental captions on the same images. And the yellow part in the middle basically uses a mixture model to merge the recommendation from these two parts. And these mixture weights gamma are the probability that this word contains a sentiment. In order to train this, we use the training signals contained in the adjective noun pairs in the Centicap dataset, and then use a cross entropy term to combine the two models and upweight the sentiment terms, and then add a regularization term to constrain the fine-tuned model to not be too far away from the MS Coco factual caption model. So that's the Centicap model in a nutshell. And how does it do? Right, so here are some sample results. There are images where it does well, right? So because of the Centicap model contains this gamma parameter, we can actually use this, interpret this as the highlighter on each generated word, where darker shades of green and red indicate basically higher confidence of positive or negative sentiment. For example, a great variety of fresh fruits and vegetables, delicious piece of cake. These are look fairly appropriate. So what's informative and memorable for me are actually the failure cases. We can see on the right-hand side that we can see the machine consider this a happy man flying through the air, or a dead man doing a clever trick. So we can see the model comprehends the image, or it, the CNN comprehends the images, and the sequence model spits out like plausible, grammatically correct sequences of word in the right sentiment, but obviously it's not informed by common sense. And you may say, what about evaluation? So we perform automatic evaluation as the general sentiment captioning task using n-gram metrics. We also design human evaluations on Mechanical Turk. One surprise observation that we got is before we evaluate the quality of captions, we asked Mechanical Turkers to say whether like captions of both sentiment polarity are appropriate for each image. And they say yes, basically give for the same image, Turkers consider both positive and negative captions to be equally likely. So here is an example MTurk questionnaire for ratings sentimental captions. So they are asked to tell us which of the caption is more positive or more negative, which one is more interesting, and then whether they appropriately describe the image. I omit the detailed statistics here, but our main observations is that the Centicap sentences express stronger and appropriate sentiment without sacrificing the descriptiveness of the image. Moving on from sentiments, right? Sentiments is only one case of stylistic options that are very simple or simpler than other alternatives. In general, one can think of style as how meanings are communicated, and also as consistent and distinguishable linguistic choices, or how authors shape text, meaning in context, meaning that style and meaning are not completely separate. So here's an example. For example, puppy carries a positive connotation, but that animal carries a negative connotation. By changing the linguistic style, the meaning of the captions, and therefore the intention towards the image is also changing. So for this part of the work, we tackle several computational challenges and representational challenges. The first one is whether or not style is recognizable in one single sentence. The short answer is no, right? So in the rest of this work and evaluations, we claim that, for example, romance needs a development. And if we only have one sentence, we can perhaps distinguish whether the sentence is likely to be from a story or not. So we call it story-like, but not romantic. The second challenge is that, as we saw in the Centicap work, there are lots of style text, but they're not associated with image content. How do we make it relevant for given images? And ideally without collecting 500,000 of them. So the data set we used for this work and has settings for training is two separate collections, 500,000 MS COCO images in training and validation set, like many other work. The second data source is the book corpus data set, which is also then being recently used, for example, by the group in Toronto, consisting of romantic novels, and we extracted about 500,000 sentences from these novels, cleaning up, like eliminating really short sentences. They are from 1,500 different books. So here is a 10,000 feet view of the semantic style model, as we call it. The key step, in our opinion, is to decouple image comprehension and stylistic language generation. Since our training data is separate, it calls for basically a multi-step generation process. In here, we use FrameNet, which was proposed by Baker et al. In the late 1990s. We first convert an image into a set of FrameNet key terms. In here, the key terms are the nouns in the image, and also what's called verb frames. For example, in here, the train is stopping in the station, or is standing in the station. So both stopping and standing would correspond to a more general placing verb frame. And then the second step is to generate the corresponding caption in different styles, such as story-like or factual, from the semantic FrameNet terms. The advantage of such a separation is that it allows us to train without aligned language data. So using MS COCO, we process the ground truth captions to extract these semantic terms, including FrameNet, verb frames, and nouns, and then train a CNN RNN architecture to generate the list of semantic terms. And separately, we either use MS COCO or the style text to generate a whole sentence from the short list of semantic terms. So in other words, switching of style can be simply achieved by switching a training corpus. And in this work, by the time we did this work, attention mechanism is widely used in NLP, and we have incorporated it as well. But the basic model architecture is still recurrent net. So here are some results. So for underneath each image, we have printed out the corresponding story-like caption and then descriptive caption trained on MS COCO. We can see that the success cases tend to use more interesting verbs. For example, the horse carriage and charge down the street. And uses past tense and uses sequence of actions such as a man water skiing and then he sobered. And they also tend to provide a first-person perspective, as is common in romance novels. So there are interesting failure cases as well. On the bottom right is my favorite failure case. The story goes, I will be in the juicer with a glass of orange juice. It is entirely plausible if this were a sci-fi. Again, a failure of common sense. We'll get back to this point a bit later. But for now, we will talk about the evaluation in this work. So evaluating romance is certainly hard. So we have two sets of evaluations. The automatic evaluation include Ngram metrics, but also style metrics using the style classifiers and language models. Our human evaluation, as one example shown on the right, evaluates descriptiveness and also whether the caption look like part of the story. We found that since the same style model is significantly more descriptive than other methods of style, while producing a similar quality of story-like captions. The intermediate representation is important, as found out by several of our ablation studies. So having covered the first two parts of the work, trying to generate a sentence for an isolated image, we will now move on to the third work, which we call transform and tell, that deal with news image and articles. So the specific, so here's an example news image in New York Times in June 2020. We feed this image to one of the caption generators online trained on MS COCO. It says a group of people walking down the street. In blue is the caption that are written by the New York Times journalist. It says on Italians' Liberation Day in April, residents of Milan place flowers in memory of the partisans who died during World War II. The rank of those who remember the war have been diminished by the coronavirus. This particular caption contains place names, proper names, entities, events, and also intentions and reasons. So we desire to get closer to what the journalist can do and generate captions that are aware of these real-world events and entities and places and people. So our training data in this work is a collection of New York Times articles consisting of 800,000 articles and twice as big as our closest prior work. The aim is to generate captions that are linguistically diverse, contextualized, and ideally we can do so with end-to-end training. These three goals are grounded on a series of prior work. So the literature on captioning is vast. So here are a small bias sample containing the particular work that has inspired the name of this work, our own stylized caption work, as well as Good News, which was a CVPR 2019 work that separates entity generation with image comprehension using slot filling. And also conceptual captions published in ACL, where it also separates the filling in of entities versus recognizing the entities from the image, and the entities are given. So here is how we do it. The model has many parts, but it basically separates into the encoder and decoder part. In the encoder part, we essentially have vector representations for the news article using Roberta or transformer version of the transformer. We represent the images using ResNet on a 7x7 grid representation, as is commonly used in computer vision. We use MTCN to extract faces and represent them using FaceNet vectors. We extract objects using YOLO and represent them again with ResNet. So there are 4 sets of different vector representations. With this, we're ready to generate or generate the caption. Before we talk about that, one representation we adopted is called Biparin Coding. It basically represents tokens in natural language, not in the unit of words, but in units smaller than frequently occurring units smaller than a word. For example, sunrise apostrophe s is broken down into 5 different parts. With this representation, we can represent 1 million distinctive words in New York Times corpus with only 50,000 word pieces. So it's called bipair. So on the bottom are inputs to the transformer that are bipair tokens. And in the middle of the transformer architecture, there are essentially self-attention that are common in transformers. And then these color links denotes multi-headed attention to the article representation, the image, the faces, and objects. The result of this is a sequence of bipair tokens that can then be reassembled into words. So how well does this do? Thanks to New York Times, we have a reasonably large corpus to compute m-gram metrics on. So in the Good News paper, the CIDR score is 13.1, and we have achieved 4-fold improvement with this end-to-end training architecture. So yes, slot filling is hard. And in this table, we can also dissect the contribution of different components. For example, the bipair encoding, allowing essentially unlimited vocabulary size, also boosted the CIDR metric by 15 points, which is the largest single improvement across any 2 rows on this table. And we're happy to see this. So Alistair has made this system available in an online demo. So if we go there, The input is a New York Times article URL. We can use some of these pre-canned examples. We click button to scrape the article. There can be multiple images in articles, but this one just have one. And it's now running the model on a server to caption the images. Once the image is captioned, we can compare it with the ground truth caption. This was, again, an example article from June of last year. And we can also mouse over each word to visualize the attention weights on different parts of the article and also images. For example, protest does zoom in on some of the people's faces and also causes of the protest, right? Minneapolis zooms in on different parts and it does not pay attention to the images much. So this makes sense. In summary, I've talked to you about 3 of our efforts towards making more interesting captions. This line of work is certainly not done, and we have managed to insert sentiments into image captions. We learned to capture images from romantic novels using decoupled content and style representation. And we capture news images by paying attention to images and faces and the news article, benefiting from better language models and paying multi-headed attention to the different multimodal resources. So since our work came out, in the past few years, there has been a lot of development in this area. So we're exciting hours are building emphatic chatbots, social media bots, captioning with personality. So if people are getting into this area right now, Facebook has a 250,000 data set on captions with personality. So people no longer need to, evaluation will be easier. This was published in 2019. So there are many open questions too, some of which could be, what do style representations and images in language share? Can we jointly model, say, language and video or image? With that, I will stop and see if there's any questions. Thank you very much.